So to yesterday session, we discussed various abnormal operating condition in the grid, as well as some of the fault condition in the grid, and how the protection systems will respond from the generator side. So how the generator protection will react to various kinds of abnormal condition. Today we talk about transformer, transmission line, and busbar protection. Again, our perspective would be from the disturbance point of view, how the protection system can react. Yesterday we had seen during system disturbances various relays which normally operate sometimes desirable, which is desirable operation, and sometimes there is a undesirable operation. We'll now see how the transformer protection behave. The most common malfunctioning, so to say, or reaction from the transformer protection system is by the restricted earth fault relay for through fault condition. When there is a fault in the grid, restricted earth fault protection, yesterday during question answer session also we discussed there are possibilities when the city performance does not exactly match when there is a through fault condition, and especially in a network where X by R ratio is high. So when the X by R ratio is high, what happens is that there is a heavy DC offset during transient, subtransient stage, and the CT performance normally exactly on HT side and LT side, unlike in generator where the line side CT and neutral side CT both are exactly same ratio, same characteristics is possible. Whereas the transformer, one is on HT side, it could be 220 kV or 400 kV, and other one is on the LV side, which could be a generator transformer, it could be 21 kV, or if it's a ICT or any other transformer, it would be different system voltage. So by construction, cities are different. Second thing is the location of the cities are different in the restricted fault. If you see for the generator transformer, maybe restricted fault may be from the getting restricted to the turret city, so you don't go into the base city. Some people go to the base city, so the restricted fault zone will be including the full winding on HV side, which is star connected, and the zone which is covered between the transformer terminal to the base city. But sometimes restricted fault is also applied to, for example, unit auxiliary transformer, where the LV cable is also included in the restricted fault. So in that case, as you see, the CT location may be in the switchgear on LV side. So not only the winding is covered in restricted fault, transformer winding, it also covers the cable or bus duct sometimes, and LV CT which is located in the switchgear. So this location of the CT and their construction sometimes results into unequal transient performance, and this being a very high speed protection, this mismatch during the transient phase can result into undesirable operations sometimes. So this is one. Yesterday we also discussed the case where it was mentioned that if the fault level changes, and if you don't revise the voltage setting of the operating coil, which is basically equivalent to changing the stabilizing resistor. In good old days, we used to change the value of the stabilizing resistor. In the numerical relays nowadays, you just need to change the voltage setting of the high impedance scheme. So that could be another reason why you need to change the setting, and this setting also need to have enough of safety margin to take care of the transient phenomenon and the offset, etc., and also the peak value of the fault current. So normally you calculate the voltage on the secondary circuit, including the cable lead resistance, CT resistance, and see how much is the maximum drop which will come across the relay. But at the same time, you have to also give up at least a safety factor of 2 in setting, so that it doesn't result into operation because of the for the through fault condition when the voltage is developed becomes in the pickup value. The third point here is the sensitivity. If you increase the voltage sensitivity, you sacrifice on the protection zone of the winding. Yesterday, Murthy had raised this issue with me regarding the how much is the winding coverage in the restricted earthfall. Why? Actually, question starts with why restricted word has been put. This is the earthfall protection. Why it is called restricted earthfall? It's called restricted because it cannot be kept very sensitive. Otherwise, you will get unnecessarily operation just now for the reasons what we discussed. And in the process, when you have a pickup value on a higher side, fault very close to neutral will not be then covered because the voltage developed will be very small and your relay may not pick up. So there is a, you can say, a blind zone very close to the neutral. Now, this is where the judiciously we need to take a call. How much security you want against how much sensitivity you want. We always talk about protection with its 3 requirements of sensitivity, speed, and selectivity. So this is a balance between sensitivity and selectivity. Usually compared to your normal percentage bias differential relay, restricted alpha relay is additionally provided because it is more sensitive than differential relay, because differential relay also has a limitation because for various mismatch conditions between LT side low current and HT side current, you need to have pickup at least of 20%. The differential current, which is the operating oil current in the percentage by differential scheme. In the generator, normally you can afford to have almost 10% pickup just to take care of the CT errors of plus minus 5% on both the sides. But in case of transformer, because of tap changing and many other natural mismatch which occurs, you need to keep a pickup which is slightly on higher side. So in transformer differential, we'll have 20% at least minimum pickup of the operating coil. So you lose actually near neutral portion of the winding sensitivity in normal differential protection, whereas it's a very sensitive and high speed protection for fault, which I would say at least on the line side 50% of the winding will be very safely covered with the very good sensitivity and high speed. But there is a limitation as far as the neutral side winding concerned, whereas the restricted alpha will give you almost 85% protection of the winding. So that way you can say it gives a better coverage as far as the winding protection is concerned. Yesterday we also had a discussion low impedance versus high impedance scheme. High impedance scheme, as just now what we discussed, it depends on the CT performance. So it is desirable that CTs are exactly matched in terms of magnetizing characteristics in each phase as well as in the neutral CT, and their transient performance also should be identical. Whereas if you go for low impedance scheme, which is a percentage bias scheme, the city requirement in terms of transient performance, knee point voltage, as well as ratio matching is not so critical. And that is the reason, as yesterday, as we said, that though high impedance scheme, as far as sensitivity is concerned and through fault stability is concerned, is a better scheme, but still we prefer to go for a percentage bias scheme because of the city requirement is not so stringent. So that way it becomes easier to um, implement the scheme. And also in the numerical relay, normally the choice of ratio matching and other things are done by software only. So all these are the advantages. In terms of the uh, restraint characteristics, yesterday what we saw for a differential relay, also there are now better multiple slope characteristics are available, which provide a good stability as far as the operation of the uh, differential relay of low impedance type, either for the main differential protection or restricted earth fault protection. So earlier trend was to have restricted earth fault relay as a high impedance relay, but now in the modern numerical relay, you can have restricted earth fault with a low impedance percentage bias scheme, thereby reducing the stringent requirement of the city. The second problem associated with transformer protection is the inrush currents. The all of you must be aware that when the transformer is energized, there is a magnetizing current which flows only on the winding from the side where you energize the transformer, and that current is having a very high second harmonic content. So typically the wave shape is a peaky waveform as shown in this diagram. This is a typical diagram. Now the quantum or the magnitude of this peak current can vary. It depends on number of factors. Um, at the point of wave, when you switch on the transformer, so R phase, Y phase, and blue phase, there is a natural 120-degree shift on the peak values of the voltages. So the point of breaker pole closing will not be exactly at the same point of the wave shape. So that is the first factor why there is always a unequal inrush current. Then that is between inequality between the three phases itself. Second is it also depends on the how strong is the source behind the transformer, from which side you are energizing the transformer. If the source is very strong, that means the impedance will be low. In that case, the inrush current will also be high. If the source impedance is high, and if the fault level is low, where X by R ratio wise, also you will have less X value. In that case, also you will have inrush current which is not so high, and it will time duration wise also it will die quickly. The third point is the inrush current can also result, it can be a result of system condition. So there are actually okay, there are actually other two conditions. One is called sympathetic inrush current. Sympathetic inrush current is sometimes when your transformer is in service and you switch on the transformer which is parallel. So the transformer which is already in service sees a sympathetic inrush current. So that is one phenomena which is again the system related. The second phenomena is due to voltage recovery, system voltage. If there is a dip in the voltage due to grid fault, and when the voltage is recovers, then there is again the inrush current experienced by the transformer which are in service, and that current will be seen only in the phase where the fault is there. So suppose there is a R phase to ground fault and the voltage goes almost to zero on R phase, and when the fault is clear, voltage will recover. So only R phase will see the inrush current and the other phases will not see. Now these phenomena basically, which is causing this uncertainty of the quantum of second harmonic, peak magnitude of the current, as well as the duration for which the inrush lasts, sometimes results into unnecessary operation, because the older relays, static relays, differential relays, etc., they were all working on the principle of average second harmonic content. So when you say I have a second harmonic restraint of say 15% or 18%, which used to be a typical setting. Good old days, we remember we used to keep the second harmonic restraint at 18%. Then with the new material, if you see what has happened is in transformer industry, you all know that now we are operating transformer at much higher flux density compared to good old transformers. So good old transformer used to have 1.4 or 1.5 Tesla as a flux density. Nowadays we go for 1.7. Now this is the curve which shows the effect of flux density on the minimum second harmonic and peak inrush current. So if you have a 1.7, so you can say the maximum inrush current could be even less than 15%. Whereas earlier, if at between say 1.4 or 1.5 Tesla, you used to get near to 20% or 18% second harmonic content. So because of the magnetic material which is being used is now different, we are facing a phenomena where the inrush current has second harmonic content which is lower. Now, why this is a problem? Because the relay has to distinguish between the inrush second harmonic, which is due to inrush current, versus the harmonic current which are present due to fault. If there is a transformer winding fault, there, especially if there is a high resistance winding fault, there will be arcing type of phenomena, and you will have current which is distorted, which will also have second harmonic. So at that time, the differential relay should not get restrained. So the main task of the relay is how do you distinguish between the second harmonic due to fault or second harmonic due to inrush current. So these are some of the issues because of which we used to sometimes get undesirable operation, or sometimes no operation because of the restraint is preventing the differential relay to operate. So there are a number of cases where people have reported that differential relay acted, but the action took place delayed. So maybe for because of the internal restraint, relay was prevented to operate, but after some time when the harmonic content became low, the block was released. Inrush, which was getting blocked, it was released, and then transformer, because there was the operating current, transformer trips as the delayed operation. So both these possibilities of undesirable operation, delayed operation, or no operation at all can be a possibility. Now this is something which has been now very nicely addressed in the numerical relay. What it does is, see, basically our old principle was the harmonic content used to be a percentage of your fundamental current. So it was basically I2 by I1 ratio. Now this I2 by I1 ratio, we used to have average of the three phases. Now you assume the condition where suppose there is a very heavy inrush current in A phase and there is a little inrush in B phase and no inrush current in C phase. So the average will become perhaps less than 18% or less than 15%, and you may not get a restraint. So this is the sort of a lacuna which has been now addressed in numerical relay, where now I2 by I1 and the restraining feature is given for each phase separately. Instead of taking the average value, we are now taking for each phase, and if any one phase detects the high second harmonic content, it will do blocking of the other two phases also. So this is called cross blocking feature. So it is basically per phase measurement, per phase analysis of the second harmonic, and also you use sometimes 1 out of 3 or 2 out of 3 mode as far as the to detect the presence of second harmonic. And further, the modern relay are also getting now additional algorithm where not only the percentage of second harmonic is taken as a criteria, it also does the waveform analysis, and from the waveform analysis also it can decide whether there is a switching phenomena which is causing the inrush current, or there is some other phenomena like city saturation or fault condition. So the malfunctioning due to various other phenomena is also prevented. So that is the advantage of this new technology. So if anyone is facing a problem of say harmonic restraint malfunctioning, it is a good idea to replace those old technology relays with the new relays with the functions of saturation detection, the cross blocking feature with a per phase detection of the harmonics, etc. So these are the advantage of the modern technology. Second phenomena which also can result into some undesirable operation or non-operation is city saturation phenomena, which is followed by the internal fault of the transformer. So what happens if the actually this was a real case study which few years back we had faced, and there is a on the LT side, LT winding was it's a 220 kV to 33 kV transformer. 33 kV side, which is distribution cable, the cable had a fault, and the cable fault current while it was being fed by a transformer, the transformer winding actually developed a fault, and the transformer differential relay was remaining restrained because it detected the second harmonic which is in the fault current being fed. And also during that fault, the one of the CT went into saturation. So when the CT goes into saturation, you again you get some sort of a peaky waveform like this. So it also results into the second harmonic generation. So these are sort of a phenomenon which are which can result into undesirable operation, as well as it can also result in undesirable restraint or delayed operation of the differential relay. This also can be overcome by the numerical relays nowadays. Modern relays actually have ability to do waveform analysis, and from waveform analysis they actually detect that this is not on account of the internal fault, this is due to say city saturation. So city saturation detection will then block the operation for a few seconds. But these are all the settings which you'll have to take care during the configuration of the relay. So this is a city saturation handling feature which can be used properly. These are some of the problem actually we face. On one hand, we say that we require special protection class current transformer for REF relay, differential relay. But with the numerical relay, if we go for cities which are not having the required knee point and magnetization characteristic, then you may land up into um, undesirable operation because of the city saturation or transient performance. Because with the reduction in the city specification in terms of knee point voltage, magnetizing current, and transient response, um, you are actually allowing city to saturate, but the numerical relay has to then take a trip decision before city goes into saturation. So the technology is now actually being developed where with the high sampling rate of the waveform, the decision to trip is actually taken before CT actually goes into saturation. So these are the advantages of the technology. There are problems which are arising out of the new technologies, and there are also solutions being developed to address those problems. So, but at the same time, we have to also appreciate that the new technology is making the protection much more sensitive, and it has better stability for the abnormal system condition. Yeah, this is the example of the wave shape where you can say there is an internal fault, and this is the actual waveform. You can say here the first peak was having a very high peak. CT is not saturated in this case. Then you can see on the second peak, the CT is saturated. CT is saturated means current has risen, but you can see the current magnitude is clipped to zero. That means the CT has saturated at this point of time. So this is the kind of wave shape when the for internal for CT saturation has occurred. And in this case, you can see that relay has operated after a few cycles when CT came out of the saturation. So this waveform is again a clean waveform, and immediately the differential relay has acted. Whereas if you have a CT saturation detection in the relay, you can avoid delay in the operations. The relay picked up immediately here itself. So these are some of the advantages. The next protection we'll discuss is overfluxing and overexcitation protection. We discussed it yesterday in the context of generator transformer. Same thing is applicable here. Over voltage, under frequency, or combination of over voltage and under frequency, because volts by hertz, V by F is the basically ratio which is directly proportional to extent of overfluxing. This overfluxing, if you see the capability, this is generally the IEC characteristics. This curve is for the generator overfluxing, and this is your transformer overfluxing capability. So you can see the transformer capability is first in terms of protection is concerned, followed by the generator. So generator tolerance is more than the transformer. So generally the V by F setting or overfluxing setting is more directed towards the capability of the generator transformer. This is the voltage and frequency capability of the generator. As yesterday also we discussed, usually up to 105% generators can operate continuously on the voltage scale. On the frequency side, yesterday again we had mentioned 47.5 on the lower side, that is 95%, and 103% on the higher side, that is 51.5. The next protection we'll have to see whether it's a transformer or generator or transmission line which reacts to various abnormal conditions is the impedance based protection. Impedance protection is very much um, applied on the transmission line protection, distance relays. It is also applied for some ICTs where there are possibilities of overload uh, during certain contingencies. So there also impedance protection is used as a backup in place of overcurrent, and of course the generator backup impedance relay. So all these impedance based protection, uh, let us see how they perform. Now, the basic characteristic of the impedance relay, as we fundamentally see, is a circular characteristic in R and X plane. So this is the resistance axis, this is the X axis, and you will have the circular characteristics of the relay. Why circular characteristic? Because as we started the protection designs, it was electromechanical, and with the electromechanical mechanism, the circular characteristic was the natural outcome of the current coil and voltage coil of the any electromechanical relay. So you used to get a circular characteristic naturally. Now this circular characteristic, if you now apply to the transmission line, for example, so this would be a transmission line depending on the line angle somewhere here. Now, this is the transmission line you want to protect. But now, if you have circular characteristic which is also going into second quadrant, it is also in the third quadrant. This particular relay, which is supposed to see only this impedance, will also operate for a parallel line or on the reverse side on the bus fault or other faults which is behind the relay. So it can operate for this side also, it can operate for this side also. So this was earlier used in a distance relay, and some of the our senior engineers will remember in electromechanical relay or even static relay, we used to call this a starter zone. So starter zone used to all encompassing zone for the grid. Anywhere if the fault is taking place, is to detect, and its objective was to do the right phase selection for the main measurement element. So the right voltage and current when you will be switched to the measurement element, which will do then the protection function. So in order to overcome this deficiency of the circular characteristic, what is done is, in the characteristic, basically we shifted the circle in towards the first quadrant. By shifting the circle to first quadrant, now we are avoiding detection of the fault in the fourth quadrant or in the second quadrant. There is a slight overlap on the second quadrant, which actually is advantage. But the limitation here was, if you have this circle characteristic, which is the Moe characteristic of the distance relay, which was very popularly used in many places earlier. This would result into a resistive reach which is only this much. So you can say, because on this circle the main focus is to choose the reactance. So the X will decide the diameter of the circle, whereas the resistance will be automatically be selected, the resistance reach by the characteristic of the circle. You had no choice as far as the deciding the resistive reach. So this was possibly not a good characteristics for a high resistance fault. So one of the action which was taken is, this circle can be then twisted, it can be tilted in this direction. So by tilting the circle towards R axis, you can increase the resistive reach. So this is one of the technique which was used. To further overcome this problem, In the modern relays, you have the quadrilateral characteristics. In the quadrilateral characteristic, there is a reactance line, there is a resistance line here. And this reactance line and resistance line both can be independently selected. So actually you can choose required R, so you can get a better coverage of the high resistance fault. Because keeping the X value same, you can change the resistance line as per the setting. So this is the advantage. This relay has only a disadvantage in a sense that for a very long line, actually if you have superimposition of fault current and the load current together, the sensitivity of the relay at the end of the line for a very long line can be a problem because of the load and fault current. But fault current will not be very high at the end of the line. Sometimes it can be fault current and load current can be very close to each other, and then the distinction between the fault impedance will be difficult for calculation. So in some application, you may then prefer to go back to more characteristics for high resistance fault for a long line, and for phase fault you prefer a quadrilateral characteristic. Now, why I have explained, and this is the way that quadrilateral characteristic can be zone 1, zone 2, zone 3, zone 4. So the point why I am explaining this sort of phenomena is you can see there are limitations of distance protections or impedance based protection relays because of the decision which is required to be taken is influenced by so many factors. The factors which are governing X factor, which how X will influence, I will explain more. And also the R value also gets influenced by many factors, and because of which each characteristics have some limitations in terms of correct operations are concerned and accuracy of the distance measurement is concerned. So many times in the different types of fault and different types of system conditions, you will have you possibly heard of underreach, overreach, or instead of zone 1 operation you get zone 2 operation, or sometimes for zone 2 fault you get zone 1 operation. So all these sort of undesirable or inaccurate measurements are possibility. So look at each of these phenomena. If you look at the fault resistance for the line, normally if there is a fault between the conductor, the fault current flows to the tower, which is earth, and flows through the tower structure to the ground, and there is a ground resistance which is called tower footing resistance. Now, if for the phase-to-phase fault, there is not much of an issue because phase-to-phase fault you have to only consider the arc resistance between the two phases. Ground is not involved in the phase-to-phase fault, so that sort of uncertainty is not there. So you can get pretty good measurement accuracy for phase-to-phase fault. Now, phase-to ground fault will have arc resistance and tower footing resistance and then earth resistance also. So you have a combination of these three. The arc resistance is normally a time-dependent phenomena, and the arc resistance value generally we use this very famous Warrington formula since decades. This has been in use, and based on this formula, you calculate how much will be the resistance of the arc. You take the tower footing resistance at 10 ohm or maximum 50 ohm, and try to then calculate the resistive reach for the line. So in the process, what will happen? The X and R value, the R, if it's a short line, R value becomes much higher than the X value. So this again causes some measurement problem, which I will explain. So this is a high resistance fault, which is one of the, I would say, um, uh, challenge to protection engineers, which has been continuing since many years, because the uh, X and R, depending on the line X and line R, the not only the load current angle, the fault angle will also vary. And because of this change in the angle, there are measurements which can be in error. So this resistive setting normally is a tricky affair, especially if the line is short. So many times we say if the line is very short, due to if there is a high resistance fault, typically if there is a vegetation fault, if there is a tree which comes in arcing distance, etc., that side of fault, you may have overreaching of the relay. Relay may trip in zone 2 instead of zone 1. Similarly, if you employ the resistive reach which is higher by using a quadrilateral characteristic for the short line, the load point of and the your zone 3 characteristic may come very close. So there is a possibility of load encroachment on the tripping characteristic, and in that case, for a heavily loaded line, you may have zone 3 relay operating, which is not a desirable thing again. So these are some of the issues which you come across. In real life, we also face the problem, what we call cross-country fault or evolving fault. What are cross-country fault? Cross-country fault means basically there are, say, two lines, and on one line you have a fault in A phase, and at some other location the second line has got a fault in another phase. So now you see there are fault currents flowing in A phase, there are fault current flowing in B phase here. So this is Rn, this is Sn. The Rn relay will correctly measure that a single phase fault relay at Sn can see it as A, B and ground, because it is having A current, it has also having B current, and it also detects it as a ground fault. Whereas the relay here will see it only on A phase. So this is one condition where there is a you can say conflict in terms of correct phase selection is concerned. Same thing happens in evolving fault. What are evolving faults? In evolving fault, maybe you start with say A phase to ground, then there is, because of the ionization of the air in the vicinity of the fault spreads to B phase. So after some time, it becomes A to B phase fault with respect to ground. And sometimes it can even result into a three-phase fault. So as far as distance relay is concerned, there is a algorithm. First, there is a measurement which decides which phase is faulty. Accordingly, it chooses the voltage and current and polarization voltage, which does the directional detection. Now, in the meantime, fault goes to, say, next phase. So then the relay algorithm sort of gets confused. While it is processing A phase to ground fault, suddenly the B phase fault has happened. So in that case, sometimes there can be undesirable measurement and relay may mal-operate. So these are some of the conditions where the measurement becomes very complex, though the modern relays are having algorithm where now all the fault loops, A phase to ground, B phase to ground, C phase to ground, A and B phase, B and C phase, means all the measurement loops are simultaneously processed. Earlier, it used to be like a switching. Depending on the as the fault develops, the voltage and currents used to switch to get switched in the measurement algorithm. So modern relays has a much higher now processing power, so you have a non-switch simultaneous measurement of all the fault loop current, but the final trip decision sometimes can become problematic because of this nature of the fault. That's why in some of the complex condition, you may have line one instead of distance protection, which is impedance based. You may have current differential relay as a preferred main one, and you go for impedance relay as a backup protection. The next issue related to again measurement error is say mutual coupling. What is mutual coupling? Mutual coupling is basically the current in one line, the magnetic field created by that current also encompasses the neighboring line conductor. So there is a reactance which you say, which we call it a mutual coupling. This sort of a induction is even more severe when there is a fault. So if there is a fault current flowing in the line, this fault current will give rise to magnetic field, and which will couple the second line also, and there will be induced current, and you may get undesirable operation of say earth fault current in this line due to this coupling. And also the measurement of the impedance or X value for the faulted loop will also be affected, and you may either get a underreach or overreach of the distance element in this particular case. So this is mutual coupling, which is very much critical in terms of zero sequence, because if there are earth fault, there will be zero sequence current flowing and mutual coupling effect will be very significant. Not so much for face-to-face fault, because there is no earth fault compensation factor which is required for face-to-face fault. So one way to tackle such a problem of mutual coupling and to avoid underreach or overreach, of course, is by way of compensating for maximum possible error which can occur depending on the how much mutual coupling effect is there. So you accordingly reduce the reach of the zone 1. Instead of keeping it 80%, keep it only 70%. Or you take the neighboring line current and give that as an input to distance relay of line 1. So line 2 zero sequence current is fed into line 1 relay, so that it can do the zero sequence compensation correctly by actually measurement of the current. It again has certain issues, so that feature is not really used in our applications for the protection, but it is certainly used for a distance to fault algorithm. All the distance relay nowadays also have distance to fault functionality, so it can be used for that, so that you get a more accurate distance for that. Yeah, so this is that feature where you use the neighboring line current into this. We talked about CT-PT transients while we spoke about differential protection of generator as well as transformer. Similarly, even the distance measurement also have problem of CT saturation during the first few cycle, and then it recovers from that. And the high-speed distance relay, which are nowadays operating in taking a trip decision in say 14 millisecond or 20 millisecond at the most, they can then experience inaccuracy due to CT transients. Basically, what happens is when the CT gets saturated, the measurement, the current magnitude falls down from the actual value. The primary current is very high, which is not getting reproduced on the secondary side correctly because of the partial saturation of the magnetic core. So the secondary current as seen by the relay will get reduced. This reduction for a few cycles, if the measurement is going on, can cause underreaching of the element because of the this measurement in current. Similarly, CVT transients. This CVT transients also is another phenomena, and all the numerical nowadays have these transient filters which can be used to suppress this transient. Basically, what happens is because of this transients, it doesn't happen in electromagnetic PT, but on the CVT secondary, normally there are transients, high frequency transient. These high frequency transients causes distortion in the voltage waveform, and since the measurement is done on the zero crossing basis, it can result into false measurement of current voltage zero, and it can cause then measurement error. So these are again some of the errors which can result into again overreach or underreach. In case of CT saturation, you will have underreach. If the CVT transients are there, there can be overreach. So these are some of the issues which we'll have to take into consideration when we suspect undesirable operation as well as inaccurate measurement of the distance. The next problem which you face with due to system is on account of what we call infeed phenomena. What is the infeed phenomena? If you have got a multi-terminal line, you see there is a generating source here, there is a line going here, and there is a tap off where again generator is connected. This problem is becoming more and more now because of, say, renewable generation which is getting connected even at HV level or even EHV level. These wind farms or solar power generation, they just get connectivity to nearest transmission line which is passing, and it then introduces the infeed. So if you have got a relay here which will, and if there's a fault here, earlier it was a straightforward impedance loop considering R and X of the line, and the current was uniformly same all throughout this fault current. But now what will happen? There is a feed coming from this generator also. So this portion of the line will see voltage drop which is due to this current as well as this current. Whereas this relay actually will not see this because it is seeing only this current. So this phenomena actually sees the impedance value which is larger than expected theoretical impedance. That means for distance element where the location of the fault will be based on ZL plus ZA, this will be actually seen to be higher by this relay because of this additional infeed factor. So this is another one. Same situation also happens if you take a tap off. What happens when you nowadays since the separate transmission line corridors are not available, or sometimes it is not economical. If there is a new load center coming up, you just take a tap from the line, create a substation. So a line may have multiple taps, and this is again happening with the renewable generation and distributed generation, especially at the sub-transmission level and transmission level, not so much on EHV line. But loop in, loop out and transition, normally if it is required to be done, it is actually a better practice to do loop in and loop out through separate circuit breaker. In short, you convert a one long line into two short lines. So that is a better practice. But to save the capital expenditure, instead of loop in, loop out with a circuit breaker, you may just take a tap off. So this again causes a problem in terms of distance relay measurement. So you need to then find a solution of addressing the fault in the tap off as well as at the remote end of the line. And you may take help of the communication scheme so that the correct measurement of the distance zone 1, zone 2 can take place. So these are some of the complications arising of the network conditions. Next, we talk about instability. Yesterday, briefly, we mentioned instability. There are three types of instabilities. There is a small signal disturbance, there is a voltage instability, and there is a angular instability or frequency instability. What is voltage instability? Voltage instability is basically is related to overloading of the line loading. So you must have heard the term of there is a surge impedance loading of the line, and there will be a point where the reactive power will increase with the change in loading. So this is basically represented in what is called the PV curve of the transmission line. So on this axis there is a power, and this axis there is a voltage. Now what happens is the line has a definite value of reactance, and depending on the length of the line and how much is the load being carried on the line, there will be a voltage drop. So you can say the terminal voltage at the sending end is this, the receiving end voltage will be slightly lower depending on how long is the line. To maintain the voltage at the receiving end, you may have to provide a reactive support. So you may insert a capacitor, static var compensator, STATCOM, at a suitable point so that this terminal voltage doesn't drop to very low value. Now, when the voltage here is less, what happens to the load which is being fed? When the voltage is low, the motive load on the bus bar or through which is being fed through ICT or any other power transformer will, if it is not voltage is not corrected, it will draw more current with a poor power factor. Motor loads typically when the voltage is low will draw more current and more reactive power factor will become poorer. So more reactive power flow occurs. Now more the reactive power flow with the X of the line, there will be more voltage drop. So voltage drop will further go down. Further then again motive load will draw more reactive power. So again voltage drop will increase. So it's like a vicious circle, and ultimately a point will come where the voltage will sink along with the active power. So active power flow actually on the line is coming down and more reactive power flow will occur, and voltage will start collapsing beyond. This is the sort of nose point of the PV curve. This nose point of the PV curve is the voltage instability point. Beyond this point, the voltage will collapse. This is exactly what has happened in 2012. When the parallel lines in a corridor has been taken out, there will be more flow on the line. Out of the remaining line, one more line trips for some reason. Then again the line loading will further go up. the voltage at the receiving end will come down. The reactive power flow will go up because the motive load will start drawing more reactive power. And finally, the voltage will go down to such an extent, and the line will be overloaded to such an extent that if the distance relay which is connected to this line, you may have tripping due to load encroachment. So what had happened in 2012 was the same situation. The distance relay had operated. It then finally isolated the complete corridor because there was and this phenomena is also called cascade tripping. So this PV curve, which is a voltage instability curve, normally the system operator has to ensure that there is enough reactive power margin so that the nose point is much away from the operating condition. So if this is the operating condition, so you can say there is a reactive margin of so much value. So this is the operating margin. When we talk about operating margin of the transmission line from stability perspective, this is what we are talking about. So when this condition happens, and it happens on the when the no circuit is out, if this is the line, one circuit out, the curve becomes like this. When two circuits out, curve becomes like this. So power handling capacity will start coming down, voltage will drop, and it will finally collapse. So the protection for the voltage collapse phenomena and actions, control actions is a separate subject which we will not discuss, because operation of the on-load tap changer, the boosting of the reactive power source by generators picking up the reactive power supply to the system, your reactive power support by way of STATCOMs. So you all must be aware now, at 400 kV level, there are many STATCOMs which are being now commissioned as a result of this great disturbance, so that the voltages can be maintained on many of the bus bar. Still in India, there are many 400 kV bus bar where during peak load condition, voltage levels are still poor at some times. So there are various control actions. There are also special protection scheme to prevent this. But main thing from protection perspective is the load encroachment characteristics. What is the load encroachment characteristics? We talked about quadrilateral characteristics. They are zone 1, zone 2, zone 3 settings, and in that setting you have a load encroachment characteristic. This load encroachment characteristic actually permits heavy drawal of the load by the line because of such instability without causing tripping. So in this zone actually no tripping will occur. Now this is very close to the R axis. That's why it is chosen carefully. This angle is chosen carefully so that the real fault condition, relay operation will not be blocked. It's only for the load condition, overload condition. How the fault is distinguished from the overload? Overload condition will normally be a three-phase phenomena where a fault can be single phase to ground or double phase to ground or three phase to ground, and there will be always a zero sequence current flowing if there is a ground fault. Whereas in the load current will be normally three-phase phenomena, there won't be zero sequence current. And in this region then the protection is blocked. Of course, if the real fault takes place during fault time, this block will get removed. So this is one more feature of the numerical relay which is now possible to have load impedance encroachment characteristics. Earlier relays of previous technology used to have an impedance blinder here. That means after zone 3 setting a characteristic, you used to have an impedance blinder so that you keep the load point away from the blinder. That is how the load encroachment was being handled. But now we can have actually this characteristic where you allow line to be overloaded for some time so that system have a special protection scheme or other control scheme which will reduce the loading to safe level, including by way of load shedding and other remedial actions which can take place. So this was the recommendation of the which was implemented in India after 2012 grid collapse. And basically this is a in voltage instability which prevents cascading of the lines to total collapse of the grid. The second phenomena yesterday I had explained about the angular instability. The angular instability is basically as a result of, as we say, inequality or mismatch between the electrical power produced by the generator and the mechanical input which is provided by the turbine. If there is a sudden reduction in active power output from the generator and turbine mechanical power being same, the machine will try to accelerate, and when the active power is more, electrical power is more, it will decelerate. This angular instability basically result into power swing. Yesterday also we saw for generator protection perspective, and this is a power swing and rotor angle swing which is slowly getting damped, and it will stabilize at the new value. And as yesterday we discussed for generator, this is an unstable swing which will keep on oscillating unless we trip the machine after a few oscillations. One of the measures which is implemented in the grid to maintain the stability, basically what is required to maintain stability, we must reduce delta P. In this diagram, this delta P, that means the difference between electrical power and mechanical power, that should be minimized. How it can be minimized? One way of minimization is by way of auto reclosure. The high speed auto reclosure, why do you adopt the single phase tripping and single phase auto reclosure? Because when the fault takes place in one phase, if you remove the line, you are actually aggravating the system condition from the stability perspective, because the impedance between two sources with X will go up, and our equation EA EB divided by X into sine delta. So X will go up, so the power flow will come down. Ability of the system to supply power will come down. So we must avoid tripping of the line. And to avoid tripping of the line, you avoid all three pole tripping. You trip only one pole and auto reclose on the same pole. So on 400 kV system, we have single phase auto reclosure. 220 kV and below, we may have three phase tripping and three phase auto reclosing. But this is basically to maintain this transient instability to take place. And this transient instability is also a function of time. As we saw here, more the fault clearance time, more will be the angular separation. Because as the machine will start accelerating, unless the fault gets clears, it will keep on accelerating. Because the turbine input and active power output, this mismatch will continue for longer time. So one of the ways of ensuring that you don't cross the unstable point, which is the this 90-degree point, is to have protection operation and isolation of the faulty element before this. This time is called critical fault clearance time. The critical fault clearance time is the maximum time beyond which system will become unstable. So this is another reason why we need to have high-speed protection system. That is also a reason if the breaker fails to operate, why do you provide local breaker backup protection or LBBU protection so that the faults can be cleared um, maximum within zone 2. So at some places, zone 2 is 0.3 second or 0.35 second, and this is basically below the you can say the maximum permissible fault clearance time from the stability perspective. Wherever it is system clearance time is even lesser, even then you will have to have a protection system in such a way that even zone 2 situation doesn't arise. That means by way of transfer trip or other communication based scheme, we must ensure that almost all faults are cleared by high speed primary protection, at the most cleared by backup protection, which is your LBBU protection, that is 200 milliseconds. So this is what is basically the overall scheme will ensure. Now, how do you handle swing? Now, this is the typical example. This is again the real life FDR. There is a long single phase to ground fault. The fault got cleared here, and you can see the system went into oscillations. So this is the oscillation where you can see the voltage is going almost to zero. So this is the point where you can say one pole slip is completed. Now, how do we tackle this phenomena of power swing? There are two recommendations. One is you have power swing blocking function in the distance relay, and there is a pole slip function on the generator protection. So the power swing blocking, basically when the power swing gets detected, it prevents line to trip, because if the line trip, this instability will further get aggravated. So one of the important requirement of the power system is when the system is unstable, you should prevent tripping of the line, because the system becomes weak when the interconnecting lines become they are isolated. So system becomes weak, and you will power handling capacity of the system will come down and instability will increase. So the and this power swing block will allow the system to recover, as we saw in this particular that swing condition, and it will become stable after some time. So during this period, when there are oscillations going on, you block the distance relay operation. Now, but at the same time, if it becomes an unstable swing, then you must trip the generator during this time when the line protection is blocked. So because generator will get mechanically stressed because of the sort of a torsional stresses which come on the shaft when the power swing or pole slip phenomena takes place. So that is the first this thing. What was the previous practice? We used to block zone 1, zone 3 and zone 2, and trip the machine, trip the line if it is in zone 1. If the swing continues and goes zone 1. So if the power swing is happening like this and goes out, within 2 seconds blocking period, it will go out. So you save the line. But if the swing keeps increasing, that means your impedance, this is a trajectory, and if it enters zone 3, it enters zone 2 and enters zone 1, then we used to have tripping. And when you used to have tripping at zone 1, then the system used to further get weakened, and then system collapse will take place. So to prevent that phenomena, the new action which is now recommend is you block the distance relay, all the zones, zone 1, zone 2, zone 3, but provide a separate out-of-step protection. This is the new feature of the numerical distance relay. The out-of-step detection feature, just now, because of lack of time, I will not explain, but it is different than power swing detection. This out-of-step tripping function. This out-of-step tripping can be a separate relay, or nowadays the modern relays have this as a inbuilt feature. Then this out-of-step, now power swing gets detected, you block all the zones, so prevent the line to trip. But if there is a out-of-step detection, you can actually trip the element of the power system which will help you in regaining the stability, at the same time preventing the shutdown. So it's not necessary that out-of-step tripping should be executed on the same line. You can trip a remote line, thereby actually cause isolation of the system. So you can say this is a controlled islanding or controlled isolation of the region or area of the power system, and decided by out-of-step protection. Which line should have out-of-step protection function, which line should be tripped, or which corridor should be tripped in case of out-of-step detection, that is decided by installing the system studies. Negative sequence overcurrent protection, partly yesterday we discussed, so will not repeat. Basically it's a unbalanced current detection. This gives to negative sequence overrating on the generators. Busbar protection we'll talk about. Basically, again, we are not going to discuss the busbar protection scheme as a whole, but sometimes busbar protection scheme can react to faults which are outside the bus fault scheme, which we call the through fault condition. Again, basically the low impedance, high impedance, same principles are used even for the bus fault differential scheme. I will not get into details of the bus fault scheme basically, but the point here is again the CT saturation phenomena. When there is a grid fault which is outside the protected zone of the bus fault, basically the performance of the CT is becoming more and more critical because of the high speed operation of the bus fault, because we have now relays, numerical relays, which can operate in say 5 milliseconds. So if the CT saturation takes place, this saturation phenomena has to be detected within 5 milliseconds, and you have to block the bus fault relay to operate because of the CT saturation. And that sort of features are now available in the what we call sub-cycle relay operation for the fault, where the trip decision is taken typically within 5 milliseconds, and we have to ensure that the time constant of the relay, which is basically time to saturate for the relay, which is less than 5 milliseconds. And for that you need to use special cities which are low remnants. Just normal PS class will not do. These are TPZ. If you have heard those specifications, these are low remnants or no remnants current transformers. So this is the requirement which we'll have to now specify going forward for 400 kV and above systems, where the fault levels are very high. There is a possibility of DC offset in the initial peak, and which can result into CT saturation in spite of the stringent specifications of the CT. Of course, going forward, the best possible solution will be to go for optical CTs, because once you go for optical CTs, all these electromagnetic phenomena you get rid of. So that will not be the issue. that is where the now slowly we are all moving to digital substitution, where even the CT and PT would be optical principle based. So that all these electromagnetic phenomena can be avoided. Local breaker backup protection we had mentioned, so I will not repeat here. LPBU scheme. So I will stop here and we'll keep time for some discussion. Yesterday, when we were discussing, someone wanted my contact. This is the email address you can note down. If you, even after the session, if you have any query or any case study you want me to comment, feel free to send a mail to me on this email address. With that, Shika, I will close here. We will go for question and answer.
Yes, sir. Yes, sir. Thank you so much, sir, for this excellent presentation. And we are open for question and answer session now. Participants can unmute themselves.
Sir, good evening, sir. Sir, a very nice presentation. Sir, I would like to understand the effect of one pole opening. Means when breaker is closed for a 100 MVA transformer, LV side one limb is not closed. So, and it is feeding the load. What is the impact on the transformer?
Transformer will not have actually a very big effect, because unlike generator, the negative sequence heating will not be so critical for the transformer if one pole is not. But when one pole is feeding, or there is an unbalance like this, of course the loading on other phases will go up. So there can be problem because of the overload on other phases, other parallel lines, etc. From that point of view, you need to isolate the condition as early as possible. So as we were discussing yesterday, either this can be detected through negative sequence protection or current unbalance monitoring on the SCADA system, and action can be initiated by manually opening the pole, or isolating the breaker by opening of the other circuits.
Sir, transformers generally they don't give any negative sequence protection.
Yeah, that's why I said unbalanced current detection is normally there normally we do it in SCADA system for including for transformers. It just it's not a negative sequence protection, but it just detects the current unbalance.
Hello.
Yeah.
Sir, I have a question. In case of 3 single-phase transformer bank, we do not have the restricted earth fault protection. That we are having only differential protection, and the CTs are located inside the delta. But the thing is, the zero sequence filtering is enabled in both H3 and H3 side. So in that case, earth fault sensitivity will be less for differential. So what be done to increase the earth fault sensitivity, because there is no RF protection in that?
Yeah, in this situation, actually, even for a single phase bank, restricted earth fault can be adopted. You on the neutral bus bar, you can have a CT connection outside the transformer, and you can have a restricted earth fault protection with either the turret CT of the single phase on line side or outside the base CT. So restricted earth fault is still a desirable protection. And the absence of restricted earth fault and differential having limitation in terms of sensitivity near towards the neutral, you have to then depend on the sensitive ground overcurrent relay protection on the neutral of the transformer. So your backup protection will have to be then kept sensitive, but the time delay will be higher. Of course, that higher time delay will not be very damaging, because fault near neutral will definitely be having a less intensity in terms of fault level. So that higher time delay in that case can be tolerated. But high-speed protection is desirable if the HT side is say 400 kV and that like that. Restricted earth fall can be easily added if you have a numerical relay. Differential and restricted earth fall both can be configured in the same relay.
I have a question, sir.
Yeah.
During the course of your presentation, you were discussing about synthetic phenomena of inrush currents on parallel effect on parallel transformers.
Yes.
Sir, can you please little elaborate, sir? How does actually one transformer is excited and other two transformers are in parallel? How the parallel operated transformers get affected?
Yes, basically, sympathetic inrush causes the voltage dip depending on how strong is the source while charging. So that momentary voltage dip and recovery due to the inrush phenomena on one transformer can cause a sympathetic inrush on the transformer which is already in service. And usually this will not be as high in terms of magnitude, but second harmonic content will be high even in that. So this sympathetic inrush phenomena is prominent if the source is stronger behind the transformer.
Good afternoon, sir. This is Pavanada from Imperial Kawai. Can you explain about the grid failure of Mumbai recently? Last year it happened. What are the causes of grid failure, or we have to take care of this setting, or some maloperation of the base? What are the basic phenomena which happened in which causes to grid failure of Mumbai?
You're talking about the recent Mumbai power system grid collapse?
Yeah, yes, sir, yes.
Yeah, of course, since the committee had investigated the matter, the report has been submitted to authorities, but I don't think the report is still in the public domain. So I won't comment on the report itself, but what is known is basically the phenomena where the remedial actions as a result of overload. Of course, the contingencies are again well known. So there were outages, then restoration of the line got delayed after the maintenance work, and then there was tripping, and after that there is a overloading on the line. Then line tripped on overload, and then subsequent conditions happened. But one point which I would like to emphasize is many times, especially on 220 kV circuit, we are still retaining phase overload relays. And this phase overload relays, see, as per the recommendation of the, if you see the even CBIP manual as well as the CA recommendation, we should have for all critical lines only distance relay as main one, main two, and overcurrent earth fault relay as a backup. Otherwise, there is an inherent backup protection in the distance relay itself. The phase overcurrent relays can malfunction during system contingencies the way it has happened in this particular case. So the number of lines actually subsequently during cascading effect tripped on phase overload relays, which are set to say 120% overload or something like that. Whereas as per our 2012 grid collapse recommendation also, the line overload in emergency condition should be at least for 10 or 15 minutes at 150% of the thermal rating of the conductor. That should be the capability of the grid to be resilient for the system disturbances. So combining the fault clearance protection of overcurrent with the overload protection, that is the basically we should not do. Fault protection of overcurrent, phase overcurrent should be separate, and overload protection and the subsequent action of load relief should be separated, so that this setting there is no conflict. In terms of special protection scheme in case of such overload, again there was an inadequate load shedding because it was only by the local action. So special protection scheme will have to be treated like more wide area scheme, where the even the remote load shedding should be able to relieve the overload on the line. So that is the comment which I would like to convey, because this is already there in public domain.
Sir, I would like to supplement, sir. As per the consequent to 2012 grid disturbance, there actually a Ramakrishna Committee guidelines recommends there should not be any overcurrent protection on EHV transmission, except directional earth fault in case a distance fail.
Correct.
So question of overcurrent protection itself should not be there for 220 and 400 kV grid connected lines.
Right, absolutely.
Good afternoon, sir.
Good afternoon.
Shivakumar, sir, from TS Transco.
Yeah.
Sir, I have a couple of questions on RF protection, sir.
Yeah.
Sir, while calculating stabilizing resistance, can we assume zero source impedance so that I can get maximum stabilizing resistance value, and I can avoid the replacement of stabilizing resistance due to change in fault current because of network expansion? This one. And what is the minimum recommended current setting for RF protection, sir? We are keeping 2% as a current setting, but through fault conditions, sometimes in some of the substations, it is getting operating.
Yeah, it is safe to actually consider as a bus bar source as an infinite bus bar. What you are saying is zero source impedance is like an infinite bus bar.
Right.
So that is very safe, but then you will be slightly be overprotective and sacrificing on the sensitivity, because the voltage setting will go higher little bit, and higher the voltage setting, your sensitivity of the coverage of the winding will be lesser to that extent. So that is the sort of compromise you will have. So it is a good idea to keep revising the, like what we do, stabilizing resistor value periodically as the fault level change, and go by the actual calculations of the voltage developed for a through fault condition, and keep revising it as the fault level changes. That is actually the better practice. The second question you said in terms of current sensitivity, again the same thing. It's a compromise between how sensitive you want to keep the protection, which also decides the coverage, how much winding will get protected. I think near neutral we need not be too much worried about. So even if you normally restricted alpha, we expect at least 85% of the winding to be protected. If that much coverage, if you are ensuring, slightly higher milliamp setting is okay.
Okay, thank you, sir. Sir, one more question, sir, regarding this sympathetic inrush current, sir.
Yes.
In some of our substations, when charging one of the transformer, the transformer which is already in service, it is tripping on HV side earth fault protection.
Yeah.
How can we avoid that operation, sir?
See, the sympathetic inrush will be an unbalanced condition, and unbalanced current will flow like a zero sequence current in the earth fault circuits. So you have to increase the pickup of the earth fault circuit. There is also now in numerical earth fault relay the harmonic restraint feature, second harmonic restraint feature. Normally, this is not known to many people, that overcurrent earth fault can also be provided with second harmonic restraint. So if you use the second harmonic restraint, you can have a sensitive earth fault protection also. So please use second harmonic restraint in the earth fault.
If there is a fault inside the winding, sir, then differential will block. This earth fault will also block, no? Then there is no backup protection.
No. The relay will be able to distinguish between the inrush phenomena and internal fault phenomena in the modern relay. So that worry is not there.
Okay. Thank you, sir.
Good afternoon, sir.
Good afternoon.
Hello.
Yeah, good afternoon.
Sir, I have a question. In auto reclose process, during that time, what is the effect on other healthy phases?
What is the effect on other
healthy phases? Suppose we have auto reclose in R phase, then during that time, if some load of that particular phase transfer to other phase, that is my question.
No, there is no effect on the other two phases, but the parallel circuit will have effect. If there is a parallel line, that means A phase current doesn't get transferred to B phase or C phase. The A phase current will get transferred to A phase of another parallel circuit.
Okay.
I have a doubt,
sir.
sir. Sir, I have
Yeah.
a doubt, sir. What is the effect of fast protection on circuit breakers? Especially if we speak about protection which operate in 5 milliseconds, what effect it will have on the circuit breakers?
Actually, that's why many utilities do not prefer to, though you may have very high speed detection of the fault and relay may issue a trip command, but we should keep sufficient time delay even on the instantaneous protections, so that you don't interrupt the current during sub-transient period. Sub-transient period lasts for 20 to 30 millisecond or at the most 40 millisecond. So at least for 2 cycle, you should not try to open the breaker. So circuit breaker opening time is normally 2 cycles. Even after the high speed relay command goes, there will be a 20-second delay in terms of interruption. Of course, after the circuit breaker opens, again it will wait for current zero to take place. So even if you execute tripping with a high speed relay, which is relay is picking up say in 5 milliseconds, there will be say another 5 to 10 millisecond if you have some many auxiliary trip relays, etc., and then there will be 20 millisecond time delay. So overall interruption time will be still 30 to 40 millisecond, which is sufficient for sub-transient peak to get reduced, and then it too should be safe for interruption of the breaker.
Sir, just now you have mentioned that we have to revise the stabilization resistance value according to through fault increasing.
Yes.
So whenever through fault is occurred, there is no voltage develop in RF. How we measure then how much voltage is developing across the resistance? Because in through fault current, there should be no flow of current in RF circuit.
No. REF circuit will have current, but it will be below the pickup of the relay. That's why you increase the voltage setting when the fault level goes up, so that for the fault which is outside the protected zone, relay should not pick up. So actually the numerical relay, that operating current, I think it's should be possible to get a record analog event. Otherwise
Relay
you
will
will
not
not be able to.
Relay will not record until it will start or something. It happened with some disturbance. We have to record.
I'd like to supplement his question, sir.
Yeah. Yeah. Go ahead.
Resistor rather than changing the voltage settings, sir.
Yes. Your voice is getting interrupted. I am not able to.
Actually, we do not see any current in RF circuit whenever if it is there is a current in during a through fault, it should be reflect some minor amount of current in loading also.
Yeah, unless you have got a disturbance record kind of thing, you will not be able to see how much current has actually flown in the operating element of REF. That you will not be able to see in normal condition, unless you have got DFR for which gets triggered by a fault.
But sir, theoretically, it should not be flow in RF circuit unless it's in.
No, as I said, no, there will be some mismatch because of either city performance. In ideal condition, what you are saying is correct, but practically there will be some mismatch, and for every through fault, there will be some current which is flowing due to the voltage developed in the all the secondary circuits which we discussed today. That means the city secondary winding resistance as well as the lead resistance of the cable, etc. So there will be a voltage developed. Only thing is that voltage developed will be less than the pickup of the relay.
Hello, sir.
Yeah.
Okay, thank
Sir,
you.
at present on distance protection for power sink blocking, we are
Yeah.
allowing to trip in zone 1 and blocking remaining all the zones. And
Yes.
we are not keeping any out of step protection.
Yeah.
If in this case, if the circuit breaker is open in zone 1, then there is a possibility of any failure of circuit breaker, sir, due to because of high voltage angle between receiving and sending end voltage.
Yes, you are right. Actually, that is one of the reason why it is not desirable to trip in zone 1, because the main consideration here is when your impedance locus is nearing zone 1, you are actually close to 180-degree opposite
Right.
phases as far as the swing voltages are concerned. So at that point, opening of the breaker is always having a risk of restrikes internally, or even the breaker pole failure can take place. So zone 1 tripping is actually not really desirable.
Okay, sir. One more question, sir.
Yeah.
In CBIP manual, there is overcurrent alarm is mentioned, sir, on power transformers. Whether that
Yes.
overcurrent alarm should be provided on HV side or LV side, or both on both sides of the winding.
It can be on both sides, especially if it is a ICT.
Okay.
So, and if it is there is a tertiary loading also, then HT side and LV side currents both can be monitored. If there is no tertiary, which is no loaded tertiary, it's only a 2-winding transformer, then overload can be monitored only on one side.
Okay, thank you, sir.
Sir, myself, Jacob, sir.
Hello.
Yeah.
Good evening, sir. I want to one question, ask to you one question, sir. Hello.
Yeah, go ahead. Your voice is not very clear.
Sir, myself, Jacob Prajapati from Power
Yeah.
Grid.
Yeah.
Sir, I want to ask one question. That if any line trips in the zone and its distance relay shows its fault location, means some kilometers.
Yes.
If there are two distance relay manual, distance are slightly different between both relays. So what should
Yes.
be the exact starting position of the fault location? What should be it should be start from zone or current or any DF start like that, so that fault kilometer should be same in both relays.
Both the main one, main two are independently measuring the fault distance to fault, and they should normally give within say accuracy of nowadays they say even 2 tower lengths. So I am not getting your question, but both will independently give the distance to fault. So there should be within reasonable matching between the two distances. Do you find that the distance measured in the two relays are different, quite different?
Yes, sir. There are too many differences. Say sometimes a line is 250 km long. One relay is giving 140 km, another one is giving 160 or 180 km like that. So what should be the
Okay.
exact
No,
start?
in such cases, basically, you will have to just go through the measurement settings, distance to fault measurement settings. Maybe as I was explaining to you, some of the zero sequence compensation factor or some other parameters, the way they are fed to the relay may not be proper, and the way they are taken into consideration for calculations may also be different. So basically, if you are not familiar, you have to ask suppliers only to help you why these inaccuracies are there.
Mostly it may be the voltage sources may be from line CVT and other relay may be from bus PP.
That also could be a possibility. Even the city cores might be different, but city cores should not matter so much. It's only normally the compensation factors, the way zero sequence and mutual effect is affecting one relay versus another relay. So you will have to then consult the suppliers, and you between the two relay, at least from experience you can see which relay is accurate, and then try to compare the other relay what is different.
But sometimes it comes at the same distance also, sir. Actually, around 50% of the line length, it comes around correct distance, and around more than 70-80% it goes very means different reading. It goes to very different reading. So, is it there any lumped element calculation or something special thing should be taken care for that?
No, it is basically the algorithm of the distance to fault measurement, which suppliers are more familiar, because the distance to fault algorithm is different than the impedance distance calculation in the protection. And the way the X by R ratio, SIR, and the mutual impedance effect, zero sequence compensation, the way it is treated in two relays, both are different. So that is basically the reason of this discrepancy between two measurements. So you basically will have to consult manufacturer only, because they are the ones who will be familiar how are they doing the calculations.
Okay, sir. Thank you, sir.
Sir, I have a question
Sir, we have a question, sir.
Yes,
hello.
Yes.
Sir, you have mentioned the restraint quality during inrush condition.
Yes.
Sir, I have questions. One, suppose there is an old transformer, and what if the inrush current is there, and maybe it is 6 to 7% of the IFL, full load current, and suppose the full load, the current will be inrush current will be suppose 10%. Then how it will protect, or suppose the transformer is already faulty and then inrush current is also there. So there is a possibilities of damage of insulation, sir.
No, all the transformers, transformer protection, if there is a fault while inrush phenomena is there, so the fault detection is a separate measurement, which is based on the fundamental current. And second harmonic blocking will not block in that case, it will directly execute the trip. So when you charge the transformer which is already having a fault, the inrush current will not prevent the relay to operate.
No, suppose, sir,
sir, in that case,
the whole protection system.
I said differential of the differential relay will operate.
Yeah, correct. Hello. And equivalent to high set, similar function is there even in the numerical relay, modern relays also, where there is a fundamental component is also checked concurrently along with the second harmonic measurement.
Sir. Hello.
Yeah.
Excuse me, sir.
We are in
the process.
There is a
process of. Excuse me, sir.
Yes.
We are in the process of changing bus bar protection, and we want to use zone 4 of the distance protection as bus bar protection. What is the ideal time for this zone 4 to act as a bus bar protection?
See, this reverse zone, which is treated as a backup to bus fault protection, it cannot be doing the same high speed clearance of the fault as the main bus fault protection will do. So it is a backup. The time delay should be less than zone 2 at the remote end. Zone 2 will be at least 300 millisecond or 350 millisecond. And more than LBVU. So between 200 to 350 millisecond, you can keep the time delay. At many of the cases, what I find in our transmission companies, I think the reverse zone setting is given as 1 second, which is not right actually. That is
no, sir. As per the Ramakrishna committee guidelines, it is a zone to 350 milliseconds. It is there.
Correct.
Prior to that, you are right, sir. It was given 1 second, and the reverse zone setting is 50% of the shortest local transmission line, sir.
Yeah. So I think we should adopt wherever it is not adopted. We should adopt the recommendation which was given by the Ramakrishna Committee.
Sir, I have a question regarding transfer protection. Can I go ahead, sir?
Yeah. Go ahead.
Yeah, actually, sir, because the protection system has become very modernized now, the transformers are fully equipped with differential protection, REF protection is there. Now the devices which are there, like the BUCOs, there, the OTI, WTI is there. There are many instances of mal-operation of these BUCOs, tripping of the units due to BUCOs or some other devices. So, like the BUCOs trip, as we know from the principle, it operates due to some major faults. So when a major fault happens, apart from the BUCOs, some other protection will surely act, like the differential or the REF or some other protection will surely act. So can I add that BUCO strip with some other protection, electrical protection, to prevent any spurious operation of the BUCOs?
No, it's not recommended because it is not recommended because BUCO's protection is not only for heavy faults where some other protection may also operate, but it also detects the faults of incipient nature or even very core faults which slowly give rise to gases, etc. You can get a BUCO's alarm and trip. Historically, there are some cases where people did try overcurrent as a check to BUCOs. So like a 2 out of 2 logic what you are suggesting. But later on that practice, because of the reliability requirement, is discontinued, and BUCOs is always considered in standalone, not interlock with anything else. So I think we should leave BUCOs independently only because it's a very versatile protection, it's very reliable protection, and it takes care of the incipient fault as well as heavy faults. So I think we should retain it as it is.
Can we add a time delay timer? Can we add a time delay timer? Can we add it for any like spurious pickup?
No, not desirable. BUCOs relay, because many times when for a heavy fault, when there is a surge, time delay will prevent actually further actually cause damage to the tank, or even sometimes tank rupture, which is a cause of fire in many cases. Most of the cases, the fire can be prevented if we can prevent the rupture of the tank at some location. And because oxygen requirement to the faulty condition where the high temperatures are there, that is available only when there is a rupture taking place, and usually results in, so no delay should be provided externally.
Sir, hello, sir.
Hello, sir.
KK Murthy speaking, sir.
Sir, actually, we are having a scheme in our station board. It is of 11 kV. From there, we are charging a step-up transformer 11 by 33 kV. Okay, sir. Then it is charging a 33 kV line, and then the line is then charging a 33 by 6.6 kV step-down transformer, and then we are having 6.6 to 415 step-down transformer. Sir, actually, I want to know that if while charging that step-down transformer 33 by 6.6 kV or 6.6 to 415 volt transformer, will my 11 kV side relay, which is the main source relay, will recognize any harmonic, second harmonic, sir?
No, I don't think, because you these Inrush currents which are on the LT, that 6.6 kV to 400 or other switching will not be causing that much problem on with your 11 kV to 33 kV main transformer, that protection. In any case, second harmonic will not result into any tripping on its own. It's only used for in differential protection for restraining. Only thing is your earth fault protection in terms of zero sequence. If it is getting transferred from third harmonic or zero sequence from load side to the HT side, usually if you have a delta winding on the step down transformer, then it will not get transferred. If you have got a star-star winding, then that zero sequence and third harmonic current can get transferred to your main transformer. So is the secondary transformer star connected or delta star?
Sir, the secondary transformers are delta star connected, but actually, sir, in the 33 kV transmission line, we have implemented an open conductor scheme in which
Yes.
we have taken along with negative sequence, we have taken undercurrent also. While charging of the 6.6 kV to 415 volt transformer or the step down distribution transformers, our line always get trip in open conductor fault. So
open conductor fault should not be on the minimum current detection. It should be I2 by I1 ratio. It's a negative sequence to positive sequence current ratio. That is the principle which is to be used.
Sir, we have used it. We have taken I2 by I1 and also undercurrent because during light load condition, it is also getting mal-operated I2 by I1. Sir.
Maybe 33 kV line, maybe unbalancing load may be there, and generally negative sequence no tripping will be given even for 400 kV system also. It is only alarms are given.
Yeah, but if it is a single circuit evacuation of a small generating station, which is
Yes,
the case in
actually it is a pump house from our generating station. We are charging that pump house around 30 kilometers from here, and we have implemented open conductor system in our 33 kV system. And whenever we are charging the transformer up in our pump house, like distribution transformer, we have 6.6 to 415. All these small transformer, our line is getting tripped in open conductor faults.
Yeah, but then you just see I2 by I1 ratio is independent. Actually, you don't need a undercurrent protection separately. I2 by I1 setting, maybe you will have to then increase.
Okay, sir.
Because I2 by I1 protection is quite a secured way of detecting open condition. So if it is maloperating for some reason, you can increase the ratio slightly.
Okay, sir.
Good afternoon, sir. Sir, whether it is recommended for 132 kV to have main 1 and main 2 protection?
We have a question. No.
Yeah, okay. I will answer this last question. So what you are saying, main 1, main 2 for 132 kV?
Yes, sir.
See, it is not mandated for 132 kV, but nowadays, depending on the criticality of that 132 kV line, for you, if that line is critical, you should always go for redundant protection scheme. And with numerical relay, you have got a multifunction relay. So nowadays, it's very easy to provide main 1, main 2 all in one protection. So that backup can also be included in that. So go for main 1, main 2. For 132 kV if it is a critical line, and you can need not have separate backup protection separately again. It can be combined with main 1, main 2 in both.
Our line length is only 14 kilometers, sir.
And that's fine. So whatever protection you can have duplicate protection if that line is critical to you.
Okay, sir. Thank you.
Sir, can you explain deviation in power frequency component functions that are being implemented in the new relays? New relays. This function is being found in new relays. Can you please explain this one?
Can you repeat power frequency? What you said?
Deviation in power frequency components function. Which is found in new relays like in NR electric relays, which is more sensitive in case of a distance protection. Can you please explain this one?
Actually, these numerical relay measurement algorithms, I am not so much familiar with each supplier because each supplier uses it. This is basically what we call frequency tracking phenomena, because all the measurements which are based on the sampling and there is a sort of a repeatability check and security checks, they need to have this frequency tracking algorithm. How it really affects the measurement and relay performance is not something which is a standard thing. So each manufacturer will have to be asked what is that effect. It is not something which is standard for every manufacturer.
Hello.
Yeah. Okay. So Shikha, do we close now? It is beyond.
So, Madam Shikha,
Yes,
KK
sir. I
Murthy
think
here.
we can conclude this session, and
Yeah.
there is a
Yeah,
last
Murthy.
question.
Sir, KK Murthy
The
is here.
last
Sir.
one.
Yeah, Murthy ji. Shikha will just take Mr. Murthy's question.
Sir,
Yes,
sir,
sure.
as far as this Bukol's protection is concerned, I have seen a very drastic episode while in Jabalpur. This earthquake had taken place, and it was 6.4 at Richter scale, and as many as 35 to 40 transformers tripped on Bukols. And on 22nd May 1997, I was executing at that time. So I took, of course, I had to stake my service and take a decision by own self, because the senior people were not there at in the headquarters who could guide me and give instructions. So I took all the indications of all the transformers, and I've asked the operators whether the Bukol's relay indication which is coming on this alarm fascia is getting cancelled or not. So everybody said, yes, sir, it is cancelled. So I said, and no other this relay has operated. So they all said, no, sir. So I took the decision, and I analyzed that, and I got all the 35 to 40 transformers switched on. Those are all EHV transformers, and whole Jabalpur region was dark. So some algorithm should be developed so as to distinguish such seismic conditions in a transformer.
Yeah, basically, this has been a problem because of mercury switches.
I don't know about Nanded. Nanded also had a severe earthquake in those days. That was in 1997-96. So this case was in May 1997.
It actually is experienced by many people where the earthquake or any other big movement is there. Basically, because of the old Buko's relay had mercury switch which was giving alarm and trip. And this, if there is a big sort of a shake-up, this mercury flow will sort of initiate a trip. So it's not really a maloperation of the Buko's detection, but it's only the mercury switch we wish to trip.
That is
now
the
new relays which are there, they all are supplied with now reed relays instead of mercury switch. So because mercury is now banned as a substance to be used, so now we get Buko's relay, and even the old Buko's relay, if somebody has still in service with mercury switch, you should replace them with the reed relays.
Okay, sir. Thank you so much, sir.
Thank you. Thank you, everybody. Thank you. We'll close the session now. Shikha, take over.
Thank you, sir.
Thank you.
Thank you so much.
Your voice is getting interrupted.
For the presentation and joining. Hello.
Yeah.
Hello.
Now we can hear.
Hello. Am I audible?
Yes. Now you are audible.
Okay. So I just want to thank everyone for their participation, and we will share the presentation after 2-3 days. So as Patki sir already mentioned his mail address, you may contact Patki sir directly through his mail ID. So once again, I would like to thank everyone, and kindly take care and stay safe. Thank you.
Thank you very much.
Thank you very much.
Thank you all. Thank you.
Thank you, sir.
Sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.